Evaluating the correlations of cost and utility parameters from summary statistics for probabilistic analysis in economic evaluations. This presentation is based on our publication in the Expert Review of Pharmacoeconomics and Outcomes Research. The SARS and R code for the examples can be found in the appendices of this article. Author contributions for this article. I thank my co-authors. The outline of this presentation. I will start with the background. Health data are often correlated such that the change in one variable is associated with a change in another. For example, the incidences of severe and non-severe hypoglycemia are generally correlated in people with diabetes, and subsequently the costs and health utility decrements which are associated with severe and non-severe hypoglycemia may be correlated, too. In another example, inpatient visits, emergency department visits, and outpatient visits are all relevant cost parameters in economic evaluation, but are also often correlated for patients with various medical conditions. In economic modeling, the correlations between model inputs directly impact the variance of model outputs and may impact the expected values of model results. Therefore, economic evaluation guidelines recommend incorporating correlations between parameters in modeling. When individual level data are available, we can easily apply statistical methods that evaluate the correlations between variables. Most often, individual level data are not readily available when conducting economic evaluations, and published studies do not report the correlations of health outcomes and cost inputs, the potential sources of model parameters. We aim to introduce methods to quantify the correlations of sample means based on published data and use examples to illustrate the methods. The central limit theorem suggests that the sample mean approaches a normal distribution as sample size increases, and this theorem is one of foundations of probabilistic analysis. Therefore, we focus on Pearson correlations for estimates of continuous variables, such as costs and utilities. In Appendix 1 of our article, we provide proof of the magnitude of correlation for sample means for correlated random variables. This slide shows the proof that for correlated random variables x and y, the correlation coefficients of sample means and samples are equal to one another when x and y are drawn jointly. When samples of x and y are drawn independently, the correlation coefficient of sample means is equal to 0. Now, I will introduce implications of the proof. In probabilistic analysis, researchers use the distributions of parameter estimates. Distribution of sample means, such as normal distribution with sample mean and standard error for continuous variable, and beta distribution for binary data, as model inputs to capture the parameter uncertainty. While the distribution of samples, individual patients, can be used as model parameters for microsimulation analyses, normal distribution with sample mean and standard deviation for continuous variable, and Bernoulli distribution for binary data. Then, if we obtain the estimate of the samples or sample mean, we can use this estimate in probabilistic analysis and/or microsimulation. If model parameters are obtained from different data sources, independent sampling, there are no correlations between these parameters. When different model parameters are from the same sample and the correlation coefficients of the sample are reported, we can directly use these correlation coefficients to simulate correlated distributions of sample means in probabilistic analysis. Based on the central limit theorem, we can simulate multivariate normal data for correlated model parameters during probabilistic analysis. Now, I will introduce the method of detecting and quantifying the correlations between variables from summary statistics. When correlation coefficients are not reported, it is possible to calculate them based on the summary statistics. The mean and variance of the linear combination of two jointly distributed random variables x and y were expressed in this slide. We can use the following formula to calculate the covariance and correlation coefficient. To contextualize this formula, we can assume that x and y are the numbers of general practitioner and specialist visits, respectively, and b are the unit costs, the constants, for general practitioner and specialist visits, respectively, and ax plus by is the total cost of physician visits. I will now present the example 1, non-severe and severe hypoglycemia events. This study reported means and 95% confidence intervals of the incidence rates of total hypoglycemia, non-severe hypoglycemia, and severe hypoglycemia events. We can calculate standard errors from 95% confidence intervals and derive the covariance and correlation coefficient between the incidence of non-severe and severe hypoglycemia events. We calculated that correlation coefficient was equal to 0.19. We simulated multivariate normal distribution data for probabilistic analysis based on the estimated means and standard errors to address the uncertainty from the parameter estimates. This slide showed the summary statistics of the simulated data. We also simulated correlated Poisson distribution data for the counts of non-severe hypoglycemia and severe hypoglycemia events in hypothetical individual patients in microsimulation to capture individual variability. In addition, the probabilistic analysis and microsimulation are sometimes also referred to as second-order and first-order Monte Carlo simulations, respectively. Example 2. An economic study reported the means, standard deviations, of total costs and breakdown of costs in 5 categories: inpatient, emergency department, outpatient, home health care, and other, over a 12-month period for patients with diabetic foot ulcers among Medicare beneficiaries in United States. We found that the sum of variances of the 5 cost categories was about 50% of the variance of total costs, which indicates that considerable positive correlations existed among different cost components. The correlation matrix of the 5 cost components includes 10 unique correlation coefficients, and the exact values of these coefficients are unknown from the summary statistics. It should be noted that the magnitude of the correlation between cost components does not impact the variances of individual cost components, only the variance of total costs. Given that our main goal of incorporating the correlations between cost components is to properly understand the variance of total costs, we can assume that there is a common correlation coefficient for all cost components. We can then simulate multivariate normal distribution data, using means and standard errors, of 5 cost components with varying values of correlation coefficients, ranging from 0 to 0.5 by 0.05. In this case, when the common correlation coefficient was 0.25, the standard deviation of simulated total costs was 234.9, which was close to the standard error of total costs, 236.6, in the observed data. The precision of the estimate of the common correlation coefficient can be improved by running more simulations. In the present study, we used the simulation approach to approximate the correlation coefficient. We provided the analytic solution in another article under the assumption of the common correlation coefficient. I will present the correlation between health utilities. There are several types of common correlations of elicited utilities for different health states. First, health utilities could be elicited from a general population using time trade-off or standard gamble methods. Some individuals may report higher or lower utilities for all or many health states than other individuals as a function of socio-economic status, education, and comorbid health conditions. Therefore, positive correlations among different health states could be expected. Second, predicted utilities or utility decrements from a regression model. Some researchers used regression models to evaluate the effect of different variables, such as patients' characteristics, interventions, symptoms, and health conditions, on utilities. Correlations may exist between regression coefficients. Based on the results of the regression model, one can estimate the difference in the utility between two conditions, with versus without a health condition, or with versus without a treatment, after controlling other factors. Third, repeated utility measures. Researchers often use longitudinal studies with repeated measures to evaluate the impact of interventions on health-related quality of life, including health state utility. Utilities of an individual are measured several times, at baseline and again at different time points, with expected within individual correlation between the baseline utility and follow-up values. We performed an informal search to explore what is available about correlations between utility data in the published literature. Publications reporting the EQ5D5L values set for England and the United States did not report the correlations between EQ5D5L health states. We further reviewed 24 studies that were included in a review of disutility for hypoglycemia in diabetes. Only 2 studies reported the variance-covariance matrix of regression models in their appendices. In summary, most published studies did not report the correlations among health state utilities. I will illustrate how to incorporate the correlations of the coefficients in the linear regression model for utilities in example 3. We included 8 diabetic complications and obtained a subset of the variance-covariance matrix of utility decrements in 8 health states. We converted the covariance matrix to a correlation matrix. The correlation matrix is presented in Table 2. The correlation coefficient of utility decrement was -0.323 between the on dialysis and foot ulcer health states. The absolute values of all other correlation coefficients were less than 0.2. After obtaining the correlation matrix or covariance matrix, it is straightforward to generate the multivariate normal distribution data for utility decrements in different health states, so to capture correlations among utilities or utility decrements. Furthermore, we estimated the utility decrements given the baseline patient characteristics and joint health conditions, 2 or more conditions. In our other article, we introduced the method of implementing a univariate normal distribution from multiple regression coefficients. In the example 4, we show how to approximate the average correlation coefficients of utilities collected over time, from a study that uses the area under the utility curves method to estimate the Cowley. Hollingworth et al. Conducted a cost-effectiveness analysis alongside a randomized controlled trial that compared sertraline, an antidepressant, with placebo over a 12-week period for depression. Authors measured the EQ5D5L utilities at baseline, 2 weeks, 6 weeks, and 12 weeks. Then, the Cowley over 12 weeks in each group were calculated from the following formula. Our goal is to incorporate the correlations between utilities in estimating the variance of Cowley, but not the exact correlation between 2 visits. Under the assumption of a common correlation coefficient among visits within each treatment group, we estimated that the common correlation coefficients among 4 utility measures were 0.55 and 0.66 for the sertraline and placebo groups, respectively. After incorporating the correlation among 4 follow-up visits, We estimated that the 95% confidence interval of incremental Cowley at 12 weeks was similar to the estimate from the observed data. However, when ignoring the correlations among 4 visits, the 95% confidence interval of the incremental Cowley was markedly narrower than the observed 95% confidence interval. Therefore, the uncertainty may be underestimated. Now, I will discuss how correlations between parameters impact the cost-effectiveness results. We considered 4 scenarios to examine the impact of modeling correlations in cost-utility analysis. Scenario 1, not incorporating the parameter correlations. Scenario 2, incorporating the correlations between cost parameters only. Scenario 3, incorporating the positive correlations of costs and utilities. Scenario 4, incorporating the negative correlations of costs and utilities. We ran 100,000 simulations to simultaneously capture the uncertainty in all parameters for the 4 scenarios. For each scenario, we calculated the mean and 95% credible interval. The cost-effectiveness results are presented in Table 3. The mean model estimates, total costs, incremental cost, Cowley, incremental Cowley and incremental cost-effectiveness ratios, were similar across all 4 scenarios. The 95% credible intervals for the costs of usual care and Xie X, and the 95% credible interval for incremental cost in Scenario 2 was slightly wider than those in Scenario 1. When modeling the assumed positive correlations between the utilities in Scenario 3, the 95% credible interval of Cowley in both strategies became wider than those in Scenario 1 or 2, and the incremental Cowley became narrower. We plotted the probabilities of Xie X being cost-effective across various willingness to pay values for the 3 scenarios using the cost-effectiveness acceptability curve. The 4 cost-effectiveness acceptability curves were similar, suggesting that incorporating correlations between costs and utilities had limited impact on the overall cost-effectiveness results in this case. We provide mathematical justification to illustrate how correlations impact the cost-effectiveness results. We simplified example 5 above under several assumptions. Findings in the simplified scenario may be generalizable to most Markov model in general. We present formulae of the variance for costs, Cowley, incremental costs and incremental Cowley in the appendix of our article. The formulae on the left side of this slide are used to derive formulae of the variance of cost-effectiveness results. Now, we summarize the findings. When the correlations between cost components are positive, incorporating the correlations between cost parameters in modeling increases the variance of cost and the variance of incremental costs, compared with omitting the correlations in modeling. When the correlations between health state utilities are positive, incorporating the correlations between utilities in modeling increases the variance of Cowley, but decreases the variances of incremental Cowley, compared with omitting the correlations in modeling. According to our mathematical justification, correlations impact the variance of the incremental costs and Cowley, but not their expected values in simple scenarios. Therefore, in general, incorporating correlations between model parameters is unlikely to impact the incremental cost-effectiveness ratio, ICER, markedly. However, in a nonlinear model involving with numerous random parameters, incorporating correlations between costs and utilities indeed can impact the expected values of the incremental costs and Cowley, as well as the associated ICER. Especially when the incremental Cowley are small, any changes in the expected value of incremental cost can lead to considerable changes in ICER. Conclusion. We introduced methods to estimate correlation coefficients for costs and utility parameters from published summary statistics. Incorporation of the correlations between input parameters in modeling can improve the precision of cost-effectiveness results and increase confidence in evidence-based decision-making. The timeline of this study. Thank you.